So our next lesson on forces in general will cover the idea of elastic forces, primarily what we would call a spring. So this video will talk about 1 and 2D springs and the laws behind them and how they work, and some examples and some elementary problem solving. Okay. Hello. Now let's look today, or first look at the topic of elastic materials. Now we're going to spend most of our time studying springs, but I wanted to first talk a little bit about this general concept so we get some of the terms proper, and this will lead into work we do in grade 12. Here we have a standard elastic band, which you're used to, and you learned that when you pull on it in the beginning, it's very easy to pull. As you pull harder, it's harder to pull. The force that it pulls you increases as you go, okay? But in the general term, an object that is elastic returns to its shape after you let it go. The only time it doesn't do that is if you've pulled too hard and damaged it somehow. And we've all probably did this as a child when we stretched a spring too far and then it didn't quite return to where it should. These things, of course, can be in 2 dimensions or more. Here's a piece of exercise material which I can stretch this way, and I can stretch it this way. I can stretch it on an angle, okay? So like a drum head, okay? Or other types of exercise garments that you might wear, which stretches in whichever way you want it to. This is really a 2-dimensional spring. And one of the best examples that you've encountered in your life for 2-dimensional springs are balloons. As you blow the air up in a balloon, the skin stores the energy and pulls it along that surface, okay, which this material could be pretty much the same. But it is different if we encounter other kinds of materials. If we encounter a solid material, such as my board brush here, it doesn't change. It's not stretchable. It's not compressible. It's rigid. Now, what we find is that all objects compress a little bit when impacted, but let's leave that for a little later on in the course. So when I press on the brush here, okay, but I leave this end alone, the force I'm applying is only local to this region, and the rest of this brush doesn't really care. And we call that stress, okay? The force per unit area in this example is local, and we call that stress. If, on the other hand, we have a liquid, such as my water bottle, and we squeeze this, the entire material feels the same force, okay? And we call that pressure. And that's because inside is a fluid that cannot resist these shear forces, these pushing forces. Here we have molecular bonds, and this thing doesn't flow, you know. Whereas here, I can put a hole anywhere in this thing, and if I squeeze it anywhere, the water's going to spew out of it. Because any liquid can't resist this what we call shear forces, where they run together. That's why they flow. So, on the other hand, what you'll notice with the liquid is I've filled this thing right full, is that I can't really squeeze this thing hardly at all. It's very, very stiff. And what we find is that although liquids will flow, they don't compress very much. And this leads us into another topic, another concept of technology which we'll see in our machines unit called hydraulics, where our ability to pump fluids this way and that allows a profound type of technology that makes construction and many other industrial applications possible. So in grade 11 we deal primarily with 1-dimensional springs, and so let's focus on that. If we have a bar here and we have a spring hanging off the bar and the spring is unloaded, the position at the bottom will sit as what we call the equilibrium point. It's the point where the spring will reside if it is not stressed. If, on the other hand, we hang a mass from it or whatever and stretch the spring out a bit, the spring will come down, and there will be a distance that is from where it was equilibrium to where it is now. Now, this is not just simply a distance, it's actually a displacement, because we could compress the spring or we can stretch it. So the direction matters. Now, normally we use S for displacement. In this example, we're using X. And that's done deliberately because this is a special kind of displacement that represents only the distance, the only displacement, pardon me, from the equilibrium point to wherever it is that the spring is extended or compressed to. By experiment, you'll find that the force of the spring is directly proportional, first, to how far it has been displaced, and that the direction of this force will be opposite to the direction of the displacement. So let's think about that. If I pull the spring down with an external force, it's going to try and pull me back up again. If I compress the force, it's going to try and push me back and always get back to the equilibrium point. Forces that do that are known as restoring forces, that if left alone, they'll return to this equilibrium point. If we want to take a proportionality like this one and turn it into an inequality, we have to put in a constant of proportionality, and that is known as the spring constant. This is measured by experiment, and the units, as you might expect, would be newtons per meter. Okay, so we would say if this has had a spring constant of 10, then every meter you extend it, it's pulling back with a force of 10 newtons. So if you extended it 2 meters, it would pull back with a force of 20, and every value there in between. You know, many springs have much greater spring coefficients than that. And this is how we use springs in our calculations. And this is known as Hooke's law. And we can be pretty sure that he did it because Robert Hooke was, well, Newton despised him. And he actually hired people to go back through the literature and take out things that Hooke had claimed that Newton felt he had discovered. So since this was left alone, we can be pretty sure that Robert Hooke did this on his own. Now, the other thing we want to look at that is surprising to some people is the following. So let's rub some things out here and see what we can learn. And you might have to watch this part of the video more than once to get a feeling for what's going on. Once again, we'll have the bar here. We're going to have one spring like so, a bit of a string, and a second spring. And we're going to have some mass pulling on it. So there's a weight, force of gravity acting downward. We have a spring force for the first spring and a spring force for the second spring. So the question then is, how do we combine FS1 and FS2? Now, naturally, we could guess and say, oh, just add them. Well, it would seem like a perfectly reasonable thing to do, and we'd be wrong. Now, let's think about what happens here. First off, we know is that the tension, the pulling force from the top of the bar through to the mass is the same all the way through. Okay, so we're going to take this and say that the tension force is uniform along the cable. That's how tension forces work. If we're stretching a spring, then that is going to be stretched by this tension force. So if we look at this one here, it's going to stretch a certain amount based on Hooke's law. And then we'll come down here. Now let's just imagine for a moment we're pulling on this with a certain force, and this spring stretches. Okay. Then if we were adding them together, would this one only stretch half of it and the other one stretch only half of it? That can't be. the tension is uniform. It's all the way along, and it's equal to the force of gravity. And so what we end up with is both the spring force 1 and spring force 2 deflect or extend, let's use that word instead. As if the other was not there. Now, you can reason this out, but here's where the danger comes for the youngster learning this material. It just seems that they're in line, we'll just have to add them. But that's not valid scientific thinking. You have to think about it. And this is a really difficult thing for young students sometimes to look through, is to figure out what's going on instead of just memorizing like we've done so often in our earlier studies. But we recognize that the tension throughout this string is the same everywhere. And these springs are going to respond to that tension. And they are both going to extend by the amount appropriate, even if their spring constants are different, so that each one of these springs is extended to reflect the tension force. So putting springs in series does nothing to change the force, and they both will extend exactly the same amount as if the other was not there. Now you need to think about this, and it's nothing more than recognizing that the tension is uniform. If these two added, then the extension would be half here and half here. Okay? And if that was true, let's look at an individual case here, this particular spring here. If we use half the displacements necessary for the tension, what's going to happen then? This spring will only be pulling with half of the tension. And you don't get to do that. Okay? You can't have a section of the string here where the tension is less than Fg. It's not allowed. So if you stare at it a little bit, you can reason it through and you can figure it out if you want to. But it takes a bit of thinking. But not too much. Now let's imagine for a moment that we do it a different way. Let's suppose instead of the example I just gave, that we have a situation where we have springs like so. Here's our mass, say, and another spring over here. So we have Fs1 and Fs2. Now let me just go a little further here to alleviate extra questions that I'm not really aiming at right now. We're going to bring this right to a V. There we go. Now here, these springs are independent of each other. And so sometimes the amount of deflection in each case could be complicated if the spring constant in one is much bigger than the other one. And that can be so. But here we're going to say it is true that if these two will add to equal the tension on the cables. Okay, so parallel spring forces add. series spring forces are equal, but do not add. So we make sure they stress that they're equal. So in this case, they may not be equal. Because for a given amount of force, if this spring has to go much further down, this one's going to do more work to balance it. So there's going to be a balancing of the displacement in some way to equalize it that way. But parallel forces will add, and series spring forces, while being equal, do not add. Okay? And so those are just some subtleties to all this. But spring forces themselves are not all that difficult. We just have to remember the different directions. So there you have the basic idea of how elastic materials work. I've also shown you some examples of where this leads in the future, which we'll get to in grade 12 and beyond. And it gives you a bit of a sense of how 2D springs work as well, because they do exist in nature and are used a fair bit. Anyhow, thank you for watching.